Okay, we are now going to prove the fundamental theorem of algebra. The fundamental theorem of algebra says if P of z is a non-constant polynomial with complex coefficients, then the equation P of z equals 0 has a solution. And in fact, further, more is true. If you count multiplicities appropriately, it has exactly the degree of P solutions, but we're not going to go down that route. Proof. We're going to write our polynomial as an z to the n plus a1z plus a naught, where could be that some of the a's are 0, but the leading coefficient is not 0, and n is at least 1 because our polynomial is non-constant. So n is at least 1, and our leading coefficient is not 0. If P of z is never 0, so we're going to go for a contradiction, then the function f of z is 1 over P of z is entire. Right? Because it's never 0. Polynomials are analytic. Quotients of analytic functions are analytic on their domain. But if I'm never 0, my domain is still everything. Now the modulus of f is equal to the modulus of 1 over P of z. And that's the modulus of 1, which is 1, over the modulus of P of z. So looks something like this. And we are going to do a trick. We are going to factor out a z to the n. If we factor that out, what we're left with is going to be an an plus something on the order of 1 over z. So I'll write it out. Let's see, an minus 1 over z. I'm going to get rid of this outer parentheses. It's not necessary. Plus an minus 2 over z squared plus a1 over z to the n minus 1 plus a0 over z to the n. All right. Now what we're going to do is we're going to pick some m bigger than 1, and this m needs to satisfy m is bigger than the maximum of all of the moduluses of the form 2anj over an. Since an is not 0, this is okay to divide by it. For j is 0 to n minus 1. Now, m is bigger than each one of these expressions for each j. There's only finitely many of them. There's only n of these expressions. So the maximum exists. We just pick something a little bit larger than that maximum. And if that maximum is less than 1, we also want it to be bigger than 1. I just want to point out here that n and an are just not, n is just the degree of p, and an is just the leading coefficient. So the only thing that's varying here is the aj term. All right, so now what we're going to do is we're going to do a little bit of analysis on this term here. So this guy in size, plus a1 over z to the n minus 1 plus a0 over z to the n is, I claim, well, let me qualify something real quick. If the modulus of z is bigger than m, then the modulus of z is bigger than 2n aj over an. And so if we switch the roles of an and z, I think that shows that let's see, actually an and 2 over an and 2n over an and z, that an over 2n is bigger than aj over z. And then one more thing, if I, so, modulus of z is bigger than m, and m is bigger than 1. So the modulus of z is a quantity that's bigger than 1. So actually, more is true. If I add z's to the denominator, I'm going to increase the number of z's from 1 to n minus j of them. Then my quantity also shrinks in size because I'm dividing by a number bigger than 1. Okay, so this expression is of course going to be less than or equal to an minus 1 over z to the 1 plus an minus 2 over z squared plus a0 over z to the n. And each one of these guys shows up here is less than an over 2 to the n. Sorry, an over 2n. So how many guys do we have? We have n of them. And so what we're going to get is modulus of an over 2 here. Whew, that was a lot. So for modulus c bigger than m, this purple underlined region of the denominator is less than, or well, strictly less than an over 2. All right. And so let's keep with that. So for modulus z bigger than m, we have then what? Well, modulus of f of z we saw already was 1 over this expression, an plus, what was it? An minus 1 over z plus a0 over z to the n. Okay, great. Now, this guy here, we want to use the bounds here. So what we're going to do is, well, z, modulus of z is bigger than m. So if I take the reciprocal, we can replace that modulus of z to the n with m to the n. And that's actually going to be a strictly less than sign. And then we're going to use the reverse triangle inequality in the denominator, where here's one term and here's the other term. And usually when you use the reverse triangle inequality, you get a bigger than or equal to sign. But since we're in the denominator, it's going to preserve that less than. So we can write this as modulus of an minus modulus an over 2. Because this guy here, we just saw in size, was less than an over 2. All right, great. So what do we have here? Well, this is 1 over m to the n. Oops, it's the wrong color, sorry. 1 over m to the n times an over 2. Now, what should we take away from this? Well, beside it being kind of complicated, the modulus of z bigger than m, if we mark m here, the modulus of z bigger than m is what f is going to look like outside of the disk of radius m. It's the blue shaded region. So this blue shaded region is modulus z bigger than m. So what we just saw here is that f is bounded on the blue shaded region. But f is also bounded on modulus z less than or equal to m because that area is compact. It's a closed and bounded subset of R2. F is continuous, it's compact. If you haven't had that before, you'll have to take this on faith or look up a proof of that statement. So I'm bounded outside the disk. I'm bounded inside the disk. So F is therefore bounded on all of C. So F was entire, and it's bounded. By Liouville's theorem, which I can never spell, Liouville's theorem, F is constant. But what was F? Well, F was 1 over P. If 1 over P is constant, then P is constant. But we assumed that we had a non-constant polynomial to start with. So we've achieved our contradiction. So blue lightning bolt. We conclude, what do we conclude? Well, it must be that F cannot be entire, right? It must be that there's an issue with the denominator somewhere. So P has a 0. And that's the fundamental theorem of algebra.